Hello. Wow, you're fast. Welcome aboard. I haven't even got the polls on yet, and I've already got 3 viewers. It's awesome. Love it. I'm going to start the Who's Here poll as usual first. Who's here? Who's here? So you can get an idea of our community. Hello, everybody. I was saying hi to the people's names until somebody alerted me to the fact that maybe I shouldn't be saying names on here, to protect the privacy rights of students. And so where I used to say hi and then I would say the names on the polls, I'm just going to say hi, but I'm seeing you and I'm thinking about you here, and welcome. I'm just going to stop saying the names. Hopefully, maybe you appreciate that. That's for your privacy and protection, that I will no longer state names on here on the streams. And don't worry, the results of the polls are only visible through Canvas. That's not a public thing. That never gets posted anywhere, even though I'm making these videos public on my YouTube site. So your comments and your information is totally kept private for you. And the burning question on everyone's mind is, what's the temperature in the college math cave today? And let's see, today it's 47 degrees. It's still freezing in here because it's like, I don't know, it's just a cave and it's not that sunny today. And so maybe I'll keep my sweater on for this YouTube live. See lots of familiar names here on the word cloud. And welcome everybody. And we're going to do our usual thing to start this session out, which is make a word cloud of our key concepts, and that will give people some hints or ideas for what's on their post. Maybe one of those words will get bigger than the others, and that's because whenever that response gets repeated in the word cloud format, the repeated response gets bigger and bigger. So then I'll take one of those big words and then I'll ask you all to share an explanation or an example in your own words. And that helps us to form a nice resource for people to prepare their discussion board post, which is due tonight at 11:59 p.m. And then after we go through that part should only take maybe half an hour. And this is based on your input from today's Zoom sessions. The next thing we'll do is we'll have a brainstorm about what we should talk about more. A lot of people have told me that they're just not sure where to start with their question asking, especially early in the week. And so the brainstorm mode allows people who have a well-formed question or idea to put that in, and then people who are not sure but would still like to give some input can just vote up or down on the ideas. And so that brainstorm will lead us into the second half, where I'll try to take requests and be explaining concepts that people want to know more about. And then the final poll will be an open-ended chat that we will leave on to act as kind of a live chat. I see one person participating on the live chats through YouTube, but not everybody wants to log in there. And so we're going to do the same kind of thing using the poll software to, keep it open to make as much of a classroom experience as possible. So welcome everybody. I see 12 respondents here on the poll and 13 on the poll, but I only see 9 viewers. So I hope people, and actually it says it right there that my connection is unstable. And now it went away. So sorry about the choppy internet, but we're exploring uncharted waters here with everybody going online in spring quarter. So I think that the bandwidth is being taxed pretty hard. If it is choppy, it's being recorded, and hopefully on the playback it's less choppy, especially if you play it back and you pause it to allow it to buffer for a little while. That should clear up the choppiness. So maybe as you play the video back and review what was done, that will help you out there. Okay, let's get started with a word cloud of key concepts for the week. So I'm going to switch us over to that question. And go ahead and enter up to 3 separate responses for what you saw as key concepts for the first half of chapter 2. And don't forget that if one of your responses has more than one word, you have to connect more than one word using an underscore or a tilde. Exactly, like if you wanted to say instantaneous rate of change, you have to type instantaneous underscore rate underscore of underscore change. And so that's great. If you had tangent line as your idea, you would do tangent underscore line so that it would keep that quote together. Otherwise, the word tangent and line will get broken up. And remember that I tried to set it so that you can change your results on the word cloud, but it only gives you about 15 seconds to change your result. So if you want to delete it and change it, I see that somebody's already corrected theirs. Way to go. You will have just a little bit of time to change it. Oh, I'm seeing some big concepts emerge. And that's exactly what I had made videos on this week, talking about the secant line and the tangent line. The instantaneous rate of change, which is the slope of the tangent line, and that's the derivative. That's where the magic happens. That whole time in chapter 1, when we were writing state equations in the form x prime is equal to and y prime is equal to, the x prime and the y prime were the derivatives. And now we're diving deeper into more of an algebraic and geometric understanding of the actual definition for those rates in the state equations. So it should be a lot of fun to talk about those this week. I'm seeing some excellent concepts emerge. And so if you're somebody who kind of is hesitant for your concept post and you're not exactly sure what you want to post, you can always come to this resource of this word cloud and just pick 3 of the large things. And those are probably spot on as I'm seeing here emerge. Those are exactly the big concepts for this week. And we can talk about how that ties in with linear approximation. We can talk about examples where we illustrate the derivative in terms of variables other than time, because in modeling, the independent variable is usually time, but the theory of derivatives is applicable to all functions with any type of input and any type of output. So we'll definitely go into those. And that's great. Okay, I've got 26 results so far, and the biggest ones here are derivatives, secant line, and tangent line, and average rate of change. So I'm going to pick one of those and ask people to explain that concept in their own words. But before I do it, I'll talk a little bit about what I see in the word cloud, because I see a little bit of matchy-matchy. I see 4 really big concepts, and they actually match out really well into 2 pairs of 2. Okay, so I see tangent line and secant line. Those are both types of lines. And I see average rate of change and derivatives. And those are both rates. And so we can match those into 2 pairs where we have average rate of change being the slope of the secant line. And then we have derivative being the slope of the tangent line. You see? So those are exactly the kind of things that we want you to think about this week. So you're really spot on there. And since derivatives are the limit of the average rate of change, I think I'll pick derivatives as the concept, because that's like the direction we're heading. That's the limiting concept that we're trying to get to from already having a foundation in average rates of change from pre-calculus. Now we're having those things merge together, starting to talk about it in an instantaneous way. But I think I've already said too much, because I want to hear your words about your explanation of what a derivative is in your own words. So the next thing I'll do is replace the capital word concept with derivatives in your own words and give an example. And so I'm going to turn on that open-ended poll next so that you all can dive into derivatives. That was one of the biggest words on our word cloud. Explain derivatives in your own words, or explain a derivative, or give an example of a derivative from any context that you're comfortable with. So I'll give that a little time to populate. And I think I've kind of done enough. Like, I made a video where I explained it and I was just talking about it in my own words. So I think I'll just take a back seat now and let you all drive this first part. And then in the next part, I'll ask for requests and I'll start talking again. Okay, so I'm starting to see some results come in there. Explaining derivatives in your own words, someone has said the rate of change at a given point within a function. Yeah, exactly, right. But I learned about rates of change when I was in pre-calculus. I learned about this thing called the average rate of change. And I always needed to have 2 points, right? They would give me like the x1, y1 and the x2, y2. And so that's that's what I already knew about, was doing like rise over run and calculating that rate of change there. But now all the results, all the explanations I see coming in about derivative are, one thing they have in common is they're mentioning the singular nature of the point. So it says the rate of change at a given point within a function, the slope of the tangent line with only 1 point on f of x, how a function changes at a given point, the slope of the tangent line, the instantaneous rate of change between 2 points as time approaches 0. Those are the entries so far. And most of them mention just that 1 point. And then that last entry there where it says the instantaneous rate of change between 2 points as time approaches 0, that starts to mention the limiting concept. Yeah, so keep in mind that when we go from average rate of change to instantaneous rate of change, we kind of have to mention how that happens. Like, how did you used to have 2 points and that now all of a sudden you just have 1 point? Like, where'd the other point go, right? So when you mention that there's just 1 point, it's even more helpful to mention that where that came from was you used to have 2 points. And then the difference between the 2 points, can you see my finger getting closer and closer together? The difference between these 2 points turned into 1, and then you just have the 1 point. And so it's a limiting concept. And then we got another entry coming in that says the derivative is the instantaneous rate of change at a point in a function as t gets closer and closer to 0. Right. So that description of limiting, where something's getting closer and closer to 0, is very important. One thing that I want to mention for this last concept, this last poll result that says as t gets closer and closer to 0, is that you really want to emphasize that the thing that's going to 0 is the distance between the 2 points. Like that, right? Or maybe yeah, like that. So I'm not trying to middle finger you guys. Sorry. The difference between the 2 points, or the distance between the 2 points, is what's going to 0. It doesn't mean that the input variable t has to be going to 0 itself. It can happen at any point. T equals 0, t equals 1, t equals 5. It can happen at any finite value for t. But when we zoom in on that one value, we look at that value and then another value that's sort of close to it, and then we see them as they merge together into 1. So it's delta t getting closer and closer to 0, not necessarily the independent variable t itself. So that's an important point to bring up. But thanks, I'm only able to really elaborate if I have some input from you all in the polls. And so thank you to everybody for putting in your ideas, your initial ideas early on, so that I can bounce something back off of that. Yeah, I'm not really able to teach unless I have people to ask questions, right? Or to give me their thoughts for me to add on to. So super important there. While we're still on this poll, does anybody want to offer an example? I know that on the word cloud, it had said, somebody has said that one concept is variables other than time. And you'll see that Garfinkel does a really good job of mentioning that in its own section in the book, where time is usually the independent variable when we talk about modeling, but it doesn't have to be. There could be other things that are considered there. And so if you want to share an example where the independent variable is time, or maybe the independent variable is something besides time, you can go ahead and put those in. Yeah, so what could I do as an example while I'm waiting for that? It's so cold in here. And every time I come in here, I'm like, what's the temperature in the college math room? So maybe an example for me would be like the rate of change in temperature here as a function of time, right? So every time I look at the temperature gauge, maybe it's going up or going down from the last time, and I want to know like how much is my temperature increasing or decreasing in time, or is it stable so that it's always the same temperature like a real cave? That would be an example from what I'm experiencing right now that I just came up with. Yeah, I don't see a lot of people sharing examples. That's okay. It's okay if nobody's ready to share an example yet. But when we ask for an example for each one of your concepts in your discussion board post, don't overthink it. I don't want you to be worried about that. It's just a check-in. So if you want to look through the section to find examples, that's great. If you want to search the internet or think about how this relates to your daily life to find an example, those are also great ways. If you try to do an example and it doesn't exactly pan out, that's great too, because that's an opportunity to learn. So don't be shy to branch out there and use your own example. And as I read them tomorrow and give you feedback through the speed grader, I'm happy to check in with you about your ideas. So hopefully you have fun exploring the concept and maybe relating it to something you know. Maybe people just aren't ready right now because I don't see a lot more getting added. So I think that by request, what I'm going to do now is I'm going to move on to the brainstorm where I ask people what they want me to talk more about. And that's going to be really helpful to lead me. And somebody says, I haven't read that section yet, but I'm getting closer and closer. So that's great, right? And what's happening right now, hopefully, is encouragement for you to get going early in the week. That's why I make it due so early, is because if you leave it and you ignore it, it's going to pile up into like an unapproachable mountain of math. And that's not how it should be. It should be like an enjoyable journey through math for the whole week. So hopefully this is starting to give you encouragement. I'm going to turn it over to the brainstorm now, because I think that's what a lot of people are looking for, is a way to request what they want me to talk about, or to at least see what others' requests are and maybe add in their 2 cents about what they want to see. So I'm going to let that brainstorm go, and I'm going to let people vote on that a little bit. What I'm going to do while that brainstorm is populating is I'm actually going to address one question that somebody asked me to do in the Zooms, which is question from 2.2.2. So section 2.2. And I'll try to kind of address what people are saying on the brainstorm there as I go through this exercise. So what I'm doing here is on page 71. So if you're following along, or here, I'll just give you a little minute to look at that. Exercise 2.2.2 gives you this function. First, it gives it to you with all these wacky letters like B and A in there. And then it tells you to let A equals 0 and B equals 1. And then calculate the average rate of change for a variety of values of delta t. So I'm going to go through that. And I'm just looking at the polls here, getting closer. Somebody is already extrapolating. No, students. So somebody has said, what I was just sharing seems like an example of what we're talking about, getting closer and closer to reading while placing a limit of it being asked of us earlier in the week. Yeah, I'm trying to have you experience a derivative in your learning, because a derivative is a rate of change. And so hopefully you're going to see like an increase in your learning with a high rate of change as you start to input the information. Okay, let's get warmed up with this example. Hopefully I got enough ink in here. And then while I'm doing the example on the board, if you could please keep entering ideas and keep voting on ideas entered. When I come back to the polls, I'll know what to talk about next. This is all for you. This is your time to add in your requests. So don't be shy. Please let me know what you want to see. Okay, now this exercise 2.2.2, I actually spoke directly to this type of function in my video for this week called sections 2.2 and 2.3. The thing about sections 2.2 and 2.3 is that they're so inherently linked together that I find it hard to talk about one without talking about the other. Because 2.2 kind of gives you the algebra that builds up the derivative, and then 2.3 gives you the geometric interpretation in terms of secant lines turning into tangent lines. So like algebra is the equation and geometry is the picture, and I don't like to do equations without the picture in mind because pictures really help me. I'm a visual thinker, and so I kind of combine those into one. So when you're reading it, I would say that even if you don't fully understand section 2.2, keep powering through it and then also go on to section 2.3, because to me, those two things together are like a big picture intro to the derivative, okay? So make sure that you take a look at both of them and then maybe come back around, loop around and revisit. And so I'll be mentioning the geometry of this as I go through this problem. Okay, so starting with the functional form there, let me just turn my brightness down so I get rid of the glare. Okay, looking at the functional form there, what that really is in terms of a review from pre-calculus is that we have, in this first part here, we have a rational function. Hopefully that rings a little bit of a bell. When you went through pre-calculus, you learned about the polynomials, which are combinations of various powers of the input variable. And then if you took the ratio of two polynomials, you got a rational function. So this ratio of t to the fourth divided by 1 plus t to the fourth is what's making that rational. The behavior of a rational function exceeds the possibilities of what a polynomial has to offer, because when we start to do that ratio, the function is able to have a horizontal asymptote. Okay, and so that's really the key core concept of this, is that we want a function that's going to top off somewhere. So what this function looks like here, and you'll kind of see it in the figure 2.2 right above it, is that you have a function that starts low and it kind of has a horizontal asymptote at the bottom there. And then it makes a switch, it goes up, and then it ends high, but it also has a plateau at the top. So it has two different plateaus. It has a plateau at the bottom, and then it has a plateau at the top. Those are called horizontal asymptotes in pre-calculus. What they have to do with biology is that a lot of biological processes come in the form of a switch, just like a light switch. Either it's on or it's off. Either a gene's being transcribed or it's not. Either I'm doing a behavior or I'm not doing that behavior. And so a lot of these switching, these on-off processes in biology are modeled using exactly this kind of function. You see, here's the zone where it's off, and here's the zone where it changes from off to on, and then here's the zone when it's on. Okay, the higher the power is on the ratio of those two functions, here we have the fourth power, but if we add to the fifth or sixth or seventh power, the sharper the change would be between the off zone and the on zone. And that's going to be really important later when we go into chapter 4 about the mechanisms of oscillation in our models. And so kind of getting comfortable with this functional form right now is really helpful for our modeling processes. We're gonna use this type of function quite a bit. these parameters A and B, I'll explain them a little bit here. Now you can imagine that when t is equal to 0, if I let t equal 0, I have a 0 over 1 here. And so when t is equal to 0, this whole first term is 0, and we're just left with A. Okay, so what A represents in this model is the value of the output when we're in the off zone, right? So here, this asymptote down here, this is kind of the A. That's the level. Here it says in the problem that we set A is equal to 0, and that's why it's equal to 0 at 0. But if A was equal to 5, then the horizontal asymptote, that's the level off point down at the bottom, that would be equal to 5. You see, that's like the starting, that's the vertical translation of the function. And then you see the A in here again, because they're saying you're going to multiply this term times B minus A. And the difference between B and A is how high up did it go when it switched from off to on. And so here, up here, this difference right here between the lower level and the higher plateau, this difference is B minus A. So that's why they have that multiplicative term in front of the rational function, is because they're trying to model some sort of switching process in general, where we used to be at the level A, and then we made a switch, and now we're at the level B minus A, whatever. Now we're at the level B. You see, because the difference is B minus A here, and so this topping off point here, this would be B. I just wanted to explain why he's got so much mumbo jumbo in this equation. This isn't actually how to do the problem. I'll do the problem next, but this is kind of the why behind him introducing this, is because he knows that later on, this is a very useful general model of a switching process from off to on that goes from level A up to level B. And the power on the polynomials that are forming the rational function, that power has to be the same power on top and bottom, so that we have the horizontal asymptote as t gets larger. And the how high that power is determines how steep that process will occur. So see my video for sections 2.2 and 2.3 for an elaboration on that. But now let's go into the actual problem, where we're just going to let A equal 0 and B equal 1. And then we're going to get that simplified functional form, and we're going to evaluate the average speed or rate of change over a variety of intervals. Okay, so now when we let A equals 0 and B equals 1, we get this easier kind of functional form. And here it says calculate estimates of the average speed over several intervals beginning at t equals 1 and say delta t equals 0.5, 0.2, 0.1. In my section 2.2, 2.3 video, I use a power of 3 instead of 4 because I wanted to make it a little different than your homework problem. And I also use delta t equals 0.5. So here I'll use a power of 4, like it has in the question, and I'll use the delta t of 0.1. Now on the brainstorm polls, I see 2 front runners for ideas for what people want to hear. And it says, what's the difference between t and delta t? And when do we know if we're looking for an average rate of change versus an Euler's method problem? So first, I'd like to address what the difference is between t and delta t, and then I'm also seeing something emerge that's an ask for an elaboration on the limiting nature of the derivative, what makes it a limit, and what is a limit for. Fantastic questions. Those are exactly the actual learning objectives behind this problem, and so you are just hitting the nail right on the head with those questions. So let's address those as we start to say, in the problem, t is equal to 1, and delta t is equal to 0.1. I'm going to draw geometrically what I'm doing when he's asking me to let t equal 1 and delta t equals 0.1, and that's going to highlight for you, hopefully, the difference between t and delta t, and it's also going to give you more insight into what is being limited when we talk about this rate of change being an approximation to the instantaneous derivative. Okay? So here's my function again, where I set the parameters here. So if you actually graph this on Desmos, and if you want to open up a tab and graph this on Desmos, you'll see the exact picture of this function f of t. Okay? And we're going to let t equal 1. That's the first part of the instructions. So when we let t equal 1, so let's let t equal to 1, I mean by t is equal to 1 that I literally want to plug in the number 1 into the function. Okay, so t is the value of the input in the function, and that's different than the concept of delta t that I'll explain next. So here's t, and I just want to know, like, what would happen if I plug that into that function, right? So I'm just going to evaluate f of 1 just to start us off. Okay, so I'm going to evaluate f of 1. And what evaluate means is it means to plug in a value into the input and then get the output. So f of 1 is equal to 1 to the 4th power divided by 1 plus 1 to the 4th power. So 1 to the 4th divided by 1 plus 1 to the 4th. So f of 1 is equal to 1 over 2. Okay, so classic from what we know about math before is that we're given a function, we're given an input value, t is equal to 1 on the t-axis, and then we plug it into the directions there, and it tells us that the output value right here is going to be 1/2, right? So the point 1, 1/2 is a point right here on the function, 1, 1/2, in terms of kind of an xy point. That's where we're sitting. And that happens to be a really magical spot for this function in particular. That's the inflection point. So I wonder if you were familiarized with that and when you went through pre-calculus. An inflection point is a place where a function changes from concave up to concave down. And it happens to occur exactly between the low end of the asymptote and the high end. Remember how we talked about this being kind of a biological switch from off to on, right? So here we're talking about switching from the off value of 0 to the on value of 1. And what's exactly in the middle between 0 and 1 is the y value of 1/2. And when does the function output 1/2? Exactly at the input of t equals 1. So I think he knew all that when he was giving you this problem. He's giving you the t value at what's called the half max. This is called sigmoid function sometimes, and we're looking at the input value right at the inflection point where we're halfway between the on and the off. So really the question is, how fast is this function moving when we're at the half max point? Remember, we talked about this function having a variety of different steepnesses. It gets steeper and steeper as the power gets higher and higher. And so with a power of 4, this is pretty steep, and so the instantaneous rate of change is pretty quick at that inflection point, okay? But I don't have the inner workings of calculus. I don't have the derivative rules that you'll be introduced to in the latter sections of Chapter 2 to exactly tell you what that instantaneous rate of change is. I don't have that with me right now. So what I'm going to do is I'm going to approximate it. And how I'm going to approximate it is I'm going to define a second point that is near my starting point, but it's not exactly the same thing. That's where the delta t comes in. So now we're getting to the answer about what's the difference between the t and the delta t. The t is the input value. T is the input value. Okay? And that is contrasted with the delta t, which is how far over to the right did I go when I was trying to approximate the derivative with an average rate of change. Okay, so delta t is how far the second point is from t. So there you go. That's the difference between t and delta t. T is the input value. That's the starting point for my average rate of change problem. Delta t is how far away the second point is from that first point. So I'll use a different color. so that you can kind of really see the difference here, is that if I have delta t is equal to 0.1, how far to the right would the point be if the difference between this and the second point is 0.1? It would be 0.1 away to the right. So that second point there would be t is equal to 1.1. You see, right now, the only thing I have before I have all of the calculus rules to calculate derivatives, at this point, I have to rely on what I knew before. What I knew before was how to calculate the slope for an average rate of change problem, the slope of a secant line. And for that, you need to give me two separate points. How far away from each other are those 2 points? They are a distance delta t away. So if I let delta t equal 0.1, then my second point is t is equal to 1.1. And that's because I started at the point t equals 1, and I moved 0.1 away, and so I got to the second point, which is at 1.1. And so then I have to input that into the function right here, 1.1 comma, I don't know what the y is. I actually brought a calculator today because I thought I would need one. It's in my pocket. No, that's my phone. Geez. Oh, here it is. I don't know what 1.1 to the 4th power is. So I need to break out the calculator. Okay? So now we're going to evaluate f of 1.1 so that we can get the y value here, so that I can do my rise over run deal. So that's going to be 1.1 to the 4th power divided by 1 plus 1.1 to the 4th power. And I'm going to have to crunch that number out. Okay? The same process that I'm doing now, they ask you to do in the problem 3 times, with the values of delta t being 0.5, 0.2, and 0.1. And each time, that red point is stepping a little bit closer to the black point. And eventually, when we get to what the actual instantaneous rate of change is, that is the limiting concept of the red point merging with the black point. Okay? So for now, let's approximate it by actually finding the output at the value of 1.1. Oh, I'm sorry. One more thing. I noticed the brainstorm has stopped moving, so I'm going to switch it to open-ended chat. Sorry, I should have done that a little sooner. Now I've got the open-ended chat question on, and so if you all want to stop me if I'm going too fast, or if you want to ask a question or something for what I'm doing, please throw that into the open-ended chat as I try to address the questions that were raised in the brainstorm. Hopefully everyone's following along. Evaluating the function at 1.1. So I got to do 1.1 to the 4th power. To the 4th power. Oh, geez. Great. I grabbed this calculator off the shelf. I don't even know how to use the dang thing. I'm going to use the internet instead. If you don't have a calculator, just use the internet. So I'm just going to type it into the internet. I'm literally typing this into the internet. 1.1 to the 4th divided by, open parentheses, 1 plus 1.1 to the 4th, close parentheses. The internet knows it all. And the answer is 0.594. Okay. Yeah, that's a little bit bigger than 0.5. Right, that's what I was expecting. So I've got an output at 0.594. And so you see, I was at the point 1 comma 1/2 or 1 comma 0.5. And then I just moved over a little. When I moved over to the right in the input by 0.1, I moved up by about 0.094. So I'm at 0.594. Okay. Can you really embellish the point in the 1.1? I think somebody's asking me to put a bigger point here so that they can see it better. Yeah. So the reason I'm evaluating 1.1 is because they told me to use a delta t of 0.1. So I started here, and I added this much to it, and that's how I got to the 1.1. Okay, and this is all because I want to know what the rate of change is. So what I'm going to do now is I'm going to draw this conceptual line called the secant line. And the secant line, a secant line in general, is a line that connects 2 points on a function. Right here, I have 2 points on a function. I have a red point and a black point. And so I'm just going to draw a line that connects them with this orange. You see that dotted line that I drew through it? Hopefully you can see that there. That's what's called the secant line. It's a line that connects 2 points that exist on a graph. And that line's going to have a slope. And the slope's going to be the difference in the y over the difference in the x. You can see that the difference in the y here is how much I jumped up, right? So what's the difference in the y from here to here? Or sorry, I keep calling it y, but actually the output is called f here and the input's called t. So that's the delta f, I would say, because this is f and this is t. The difference in the f is the height, the red height minus the black height. And so that's going to be this amount right here. Let's see. So hopefully the quality is okay for you. If you see a really blurry screen, you might have to wait till you replay it and let it buffer in order for you to get the best quality, but hopefully people can see this. So I'm calculating the delta f, which is the rise for my rise over run. And then the bottom half is going to be how far did it run. And that's exactly the delta t that defined my red point, right? The delta t right here is the difference. How far to the right did I go from my initial point of interest, t is equal to 1, and then I went over by 0.1, so that's equal to 0.1. The delta f here is calculated as this red amount minus this black amount. So I started at 0.5, and I went up to 0.594, so that's 0.594 minus 0.5, which is 0.094. Okay, so my difference in the rise is 0.094. The difference in the run is 0.1. And so for the final part, I guess I'll have to erase some of the screen here to get this in. I'm going to calculate the average rate of change. So the average rate of change between t equals 1 and t equals 1.1 is the change in the rise over the change in the run, which is 0.094 divided by 0.1, which is 0.94. So that boxed value there would be what they're asking for when delta t is equal to 0.1. That's the average rate of change between those 2 points. I could have done that again for delta t is equal to 0.5, in which case the points would have been 1 and 1.5. Or I could have done it where delta t is equal to 0.2, in which case the points would have been 1 and 1.2. So let me write that down on the board so that's kind of instructions of how to do the rest of this problem. You see, this average rate of change between here and here is because delta t is equal to 0.1, okay? Now, I'll write down the 2 points that I would have used if my delta t was 0.5 or if it was 0.2. So if delta t was equal to 0.5, then it would be the average rate of change between t is equal to 1 and t is equal to 1.5. Okay, if the delta t was equal to 0.2, then the 2 points would have been t is equal to 1 and t is equal to 1.2. So to really fully finish off this problem, you would have done the exact thing that I did on this board here between 1 and 1.1, using 1 and 1.5 or 1 and 1.2. using delta t of 0.1 is the closest one out of those three. So those 2 points are the closest together. And all of these are calculating average rates of change or average speeds. But if I really wanted to get a handle on what the derivative was, then I would let the limit between the 2 points go to 0. So just to check in with the polls, somebody said, please elaborate on the limiting nature of the derivative. What makes it limiting and what is it a limit for? So that's the part that I'm answering right now. Doing this exercise here and again, these are all approximations to the derivative, but they're all average rates of change because they are between two unique points, two actually different points. The limiting nature of the derivative, what's getting limited, is that the delta t is going to 0 in the limit of the derivative. Okay, so I'm going to write that down over here. Okay, so for the derivative, we set the limit as delta t goes to 0. This is really the heart of what the derivative is. It's the same concept we were doing for average rates of change, but this delta t here is smaller and smaller and smaller. So what is the limiting nature? What's the thing that's getting limited? It is okay, so it's a merging event. It's like these 2 points that used to be 2 separate points on a graph are getting closer and closer and closer together. And as they merge into just one single point, the thing that used to be an orange secant line now becomes a tangent. This is a lot better illustrated in the little Desmos activity that you'll see in my video. So if you look in the video for 2.2, 2.3, like the last third of that video is me going into that Desmos activity that I provide the link for and showing you the nature of how it's getting closer and closer. In fact, actually, I think I created a video that's just me using those Desmos activities where I'm trying to explain exactly what I'm trying to explain right now, which is that delta t is going to 0, so those 2 points are merging into 1 point. Somebody has written, is this where the concept of epsilon comes in? And yes, if you've seen calculus in other books, you'll notice that they use this little epsilon, which is this little Greek letter that kind of looks like an E. And usually in math, epsilon is used to denote a value that's getting infinitesimally small. That means smaller than the smallest thing you could ever think of. It's going to 0, but it never actually makes it to 0. Kind of like Zeno's paradox, if you want to look that one up. That's a fun one, where we're just reducing a quantity, we're making it smaller and smaller and smaller, never actually becomes 0, but it gets so close to 0 that the approximation of what the limiting thing is, the derivative, is what starts to form. Yeah, so that's the concept of this turning into a tangent line. I'm resisting the urge to draw the tangent line on the board because there's already so much stuff on the board there, and instead I'll invite you to look at the video I made for the Desmos activity where you could actually plug in this function and you could play with it and see the actual graphs, and they've laid it out really neatly so that you can see how the secant line merges into the tangent line. And then the tangent line is what describes the rate of change exactly at that instant. And that is actually what all of our models are based on. When we're writing all these models in chapter 1 that say x prime is equal to that, the x prime is the derivative. It is the instantaneous rate of change. And writing down those state equations is trying to describe how that instantaneous rate of change changes when the state value itself has some given value. It's a really interesting place to start, I think, for students, because students have been introduced to calculus for quite a while before they get introduced to state equations. So we're kind of flipping the curriculum a little bit in this book, but it really motivates you to want to learn this whole deal because it starts from a place of modeling, and that's the end goal, right? And so we're starting by giving you the end goal in mind, like, hey, look, we can predict the future. How about that? And then kind of unfurling the onion, unpeeling the layers so you can see what's behind the inner workings of that. And so that's where we are now, trying to explain what the X prime actually is. Okay, so hopefully that helped, and I feel like I answered a lot of the questions that I saw in here. The only thing that I didn't answer was somebody had said, what happened to B minus A? Because on this left board, or on this, on this board before, I had said B minus A, and B minus A was just, that was this distance between the two, the flat at the bottom and the flat at the top. The difference is B minus A. They had that written on the board, so hopefully I answered that question too. Okay, that was hopefully helpful to you. Do you want to see other things? You can put any comments into the open-ended chat if you want to see anything else. Of course, there's more I could say, but I don't want to overwhelm you with information so early in the week. And so really, I heard a lot of people say that they felt like they were behind, that they were constantly feeling like they weren't caught up. But if you're here and you're paying attention to the readings and starting to engage with the videos and stuff at this point, then I think that you are doing a great job. I think you're exactly where you need to be. And so you don't have to have done everything by Tuesday, of course. That would be impossible. So I'm not going to do any more problems yet. Usually I save those for Thursdays to see when you're ready for them. But does anybody have any other questions about the concepts, how we introduce those two types of lines, secant versus tangent, and the two types of rates, average versus instantaneous? If you have any more questions, I'll give you a minute to throw them into the chat box. Otherwise, I'll just close it out. And we can do this again on Thursday and probably have more questions, more concrete exercises that people want to go through. While I'm waiting for questions to come in, I'll just show you that on the same page, there's this yellow part down at the bottom, and that's where they define the instantaneous rate of change as the limit as t goes to 0 of the change in the output divided by the change in the input. That's exactly what I was trying to say, is this definition here. Can you explain integrals more? Ooh, okay, so I will explain integrals a little more, but for those who might be feeling a little overwhelmed, I will say that what I'm gonna say next is covered in section 2.6, and we're gonna do that next week. Okay, so it sounds like some people are ready for a peek ahead into next week, and I'm happy to do that. But for those who might be already feeling a little frazzled, don't worry if you don't absorb this next part fully, because this is gonna be a peek into next week's curriculum. But also, as I explain integrals a little bit, it's a good chance to explain when a problem is looking for average rate of change versus Euler's method, because what an integral is conceptually to us is it is very much related to what we learned at the end of chapter 1 about Euler's method, okay? So when someone's asking you to calculate a derivative or an average rate of change, that's the speed that we're asking for there. And when someone's asking you for an integral, that's the opposite. That's taking a derivative, like having a function and taking its derivative is one thing, but having the derivative and trying to realize what the function was based on that is the backwards of it. And so, yeah, so somebody's entering a comment here that says in the previous sections, it was saying that a trajectory is also called the integral or solution curve. So I was curious of the overlap. That's great. That's fantastic. Exactly. This is how it's tying in with what we were introduced to at the end of chapter 1 with trajectories, and maybe they had called the trajectory an integral curve or a solution curve, and I'll explain the reason of that right now, knowing that this is all a peek ahead into next week's learning, okay? Okay, so for this, I think it would be helpful to have an example from what we've already learned in chapter 1. And so what I'm going to do is I'm going to throw up a really simple example of a state equation from chapter 1. This might be the simplest example that we can do, where we have from chapter 1, the very simple positive feedback loop where the instantaneous rate of change of x, or the derivative x prime, is equal to the current state itself, x. So another way to say this, which aligns it with the definition of the derivative that we were just learning right now, that x prime is dx dt is equal to x. Okay, so this is just another way. This is a different type of notation. Some people can express the derivative as x prime. That's what we were doing in chapter 1. And then sometimes it's nice to write down dx dt. The nice thing about this type of notation is it really specifies for you what the derivative is in terms of the slope. Remember, it's the slope of the tangent line, and a slope is a rise over run concept. And so the rise is the difference in the output divided by the run, which is the difference in the input. So this notation here really emphasizes what I was saying earlier in the class. The input variable is time, and the output variable is x. Okay, so this statement here emphasizes the input is t, and the output is x. So that I can see that the instantaneous rate of change is dx dt. It's the rise over run, and that kind of coincides with our whole concept of the time series. So on a time series graph, the input variable is on the horizontal axis, and the output variable is on the vertical axis. Now, why was somebody even bringing up integrals now when we don't, we just started talking about derivatives? So integrals are when you have a derivative and you want to go backwards and say, where did that derivative come from? Then you would take the integral, okay? And that's actually exactly the situation that I'm in right now, because I have the derivative. Like, you told me what x prime is, but now you want me to draw a graph of x. Well, how am I supposed to draw a graph of x? I only know what x prime is. So in order to figure out what x is, only knowing what its derivative is, that's why we have to do the integral. And in order to approximate the integral, we're going to do something that's very similar to what we did to approximate the derivative. What we're going to do is we're going to say, okay, what's your rate of change right now? It's equal to your state. Okay, so if I assume that you're a line and you're going at this constant rate of change for some little amount of time, I'm just going to travel along the line for that amount of time, and then I'm going to see where I ended up. And that's the Euler's method that we learned about before. So what I'm going to do on the board here is I'm going to implement Euler's method, but at the same time, I'm going to try to tie it in with doing the opposite effect of a derivative, okay? So basically, it was called integrating the equations, all right? So Euler's method is conceptually integrating the state equation. Okay, and this gets back to the point that somebody had asked on the brainstorm, which is like, when is a problem looking for me to do an average rate of change, and when is it looking for me to do Euler's method? So what Euler's method does is it integrates up an average rate of change. So if you're asked to do Euler's method, you will have been given a state equation. I can't do Euler's method unless I'm already given the derivative. But for an average rate of change problem, they're usually asking you to find the derivative. You're usually given the original function x, like we were in the last problem. We were given an f of t. And then we were asked to calculate an average rate of change to approximate derivative at various points. So those two things go hand in hand, but they're kind of the opposites of each other. Somebody's asking, is dx standing for delta? So change in x? Yeah. So someone's asking for a little more about this. So let's relate this back to what we had just done before. Remember that, recall, the derivative is a limit. So x prime is the limit as the 2 points get closer and closer. So the limit as delta t goes to 0 of the difference on the top divided by delta x. And so the delta x on the top is that's the rise. That's the rise. The difference in the outputs. And the delta t on the bottom is the run. Okay, so the derivative is a rise over run concept where we have a difference between two output points, and then we're going to divide it by the difference between two input points. If we do that again and again for smaller and smaller delta t, so as those two separate points merge into one, that's when those deltas turn into d. That the d there instead of delta is trying to communicate that this limit has already been taken. Okay, so like I already merged the 2 points so that the difference between the x values is really infinitesimally small, and the difference between the two t values is also infinitesimally small, but I took the limit of the ratio in a way that makes mathematical sense. So that's what the whole theory of calculus is meant to define, like a rigid foundational definition, so that we're just not playing with 0 over 0 and we're like, yeah, 0 over 0, I totally know what that is. You need to really tell me exactly what you were doing when you got yourself in that situation. That's what I'm defining here. And then you get the state equation. Okay, going back to the difference between average rate of change and Euler's method, if I was doing an average rate of change problem, I would have given you the equation for x. If I gave you x of t and I told you x of t is equal to e to the t, maybe I would say, then I could say, go ahead and calculate the rise over run for a variety of different points, make those points get closer and closer together, and then see what the derivative looks like. That's what I would do if I was doing that derivative type of problem. But here in the state equation, and this is where we're going to move to in general for the rest of the class beyond chapter 2, is that we only know what the derivative is. We don't know what the functional form of x of t actually is. We just know how the output is related to its derivative. It's a really interesting question to pose, because I really want this graph. I really want to know what the solution is. but you're just telling me what the derivative is. You're not telling me what the actual function is. So that's a question for integration, which is going to be similar, the same thing as Euler's method for the purposes of our learning. So let's practice doing that again. This will be a good review of Euler's method, and it'll also get your what your appetite for what's coming in section 2.6 on integration. Okay, we're given the derivative. Let's choose a starting point, and then let's just keep moving over by little bits of delta t, and let's integrate the state equation. That's what we're going to be doing. Okay, so maybe we're going to start here. Maybe let's use a starting point. X0 is equal to 1. That's the initial condition. Okay, so let's say that at time is equal to 0, I'm going to start at the value x0 is equal to 1. That's what we were calling our initial condition for Euler's method. And knowing that I'm starting right here, x is equal to 1, I want to make a prediction for what's going to happen next in time. And you're telling me what the rate of change is. You're telling me how that's related to the output here. So I'm just going to take it one step at a time with Euler's method. Okay, so I'm going to do that over here on this side. And I'm going to implement Euler's method. And that is conceptually what you're going to be doing in section 2.6 when it asks you, when it talks about all those Riemann sums and stuff like that. Doing a left-hand Riemann sum, if you've heard of that before, is exactly an implementation of Euler's method that we saw in section 1.7. Okay, so we're going to start with t is equal to 0 and x of 0 is equal to 1, right? And then we're going to do a linear approximation. That's another thing they talk about in this section, is we're going to say, okay, let's pretend the actual solution curve here is a line with a constant rate of change. If I'm starting here, how fast am I going? The answer is in the state equation. You're going to be going at the speed equal to the state. And so you can find the rate of change. The rate of change is x prime is equal to x, and so that's equal to 1. The reason it's equal to 1 is because I'm literally at the state x is equal to 1 right now. Okay? So I'm starting here, and I'm going to move like a line. I'm going to move with a speed of 1. But how long should I move that way? Because I betcha the answer here, the true answer, is probably not an actual line. If it was a line for all time, then its x prime would have been equal to 1. Remember, I had said that in another video. But its x prime isn't equal to 1. It has feedback in it, and so its x prime is equal to x. So as I travel along what I think is a line, I can only do that for a minute, and then I should stop and be like, wait, what's my rate of change now? And then I'll have a different rate of change. So how long I'm going to assume that I'm acting like a line is a time length called delta t. Okay, so I'm going to assume constant change for delta t is equal to 0.1. Remember when we were doing Euler's method, we kept saying that all those solutions are approximations, and the approximation gets better and better as we make a smaller and smaller delta t. So I'll use for my example, delta t is equal to 0.1, but just so you know, the true solution would only be found if I let delta t take a limit and go to 0. It's the same limit as delta t goes to 0 as we see in the definition of a derivative. Well, I can't actually let delta t equal 0 or I'll never get anywhere. So I have to let it be a small number, but something greater than 0. And if I do let it equal 0.1, then it means how far did I go? Far did we go? Well, we went at a rate of x prime. So we went at the rate dx dt. But we went that far for delta t time. So we went 1 times 0.1 which is equal to 0.1 x units. Okay? Hopefully this reminds you of Euler's method, because it's exactly what Euler's method is. And it's also exactly what a Riemann sum is going to be when we talk about that being an approximation to integrals in section 2.6. Okay, so how far did I go in the x is 0.1, which means I went from here to here. So here is times 0.1, and I went up by 0.1. See, so I traveled along this line for that little bit of time. But now that I'm at that time, now that I'm at that state, x is equal to 1.1, I should probably reevaluate how fast I'm going. Because I'm not going at a rate of 1 anymore. You see, now I'm going at a rate of 1.1. So I actually am going faster than I used to be going. So now I have to do this whole Euler's method thing again. And I'll have to do it again and again and again. And so now I'm going to start at next. So next step. Here's me doing the next step. T is equal to 0.1. X of 0.1 is equal to 1.1. And the rate of change is still related in the same way. The state equation itself didn't change. It's just the evaluation of the state equation, x prime is equal to x, is now 1.1. Now my delta t is still the same. It's 0.1. But how far did we go is, got to recalculate this. We were going now at a rate of 1.1 for 0.1 seconds. And so that's equal to 0.11. 0.11 is just a little bit faster than the 0.1 that we had gone before because the rate's a little bit faster. So now when we get to time is equal to 0.2, we've gone up. I'm overemphasizing it. It's not to scale, but now we've gone up so now we traveled from 0.1 plus 0.11 is equal to 0, or sorry. Now we've gone up by 0.11, so we're at the point 1.21. See, so we've gone up from 1.1 before to 1.21 above here. And then you can see that if we reevaluated how fast we were going, now that we're at the state 1.21, we would be going at an even faster clip. We'd be going at 1.21 instead of the 1.1 that we had before. And this is going to kind of snowball. It's really going to get out of hand. And it is, in fact, going to result in exponential growth. Because the higher we are, the faster we go. The faster we go, the higher we get. The higher we get, the faster we go. Exponential growth. So the true answer, the true solution is x of t is equal to e to the t. Whoa. This is a really sweet punchline to one of the derivative things that we're going to learn in section 2.4. So that's actually next week's reading. Sorry, I mean in 2.5. So I know there's only 5 viewers left here, but it's probably 5 of the most curious of you who are wanting to hear ahead. And so if you do have your book in front of you, if you turn to page 94, this is next week's learning in section 2.5, you'll see that the derivative of an exponential function is in fact an exponential function. So the derivative of the function is the function itself. That's really, really interesting. And there's the function out there that has that property. Some people may say that exponentials are actually defined by definition, the types of functions that obey this type of linear feedback loop in differential equations. Planning on making some videos for next week that really go into this in depth. So if a lot of this went over your head at this point, don't worry. It's just coming from some people being curious about where this is going. And so, yeah, we'll definitely revisit this one again. Okay, hopefully that wasn't too far into the future. I didn't mean to overwhelm anybody there. Remember that it's Tuesday and your concept posts are due by the end of today. So hopefully this YouTube Live helped you to get some ideas for that. Going back to the word cloud that we formed on the YouTube Live page, that's picking any three of those things would be perfectly fine choices for your 3 concepts for this week. Thanks for staying for so long. Again, I hope I helped you, and I'm going to sign off now. I'll see you all again on Thursday. Bye-bye.